by now you should already have a good understanding of this diagram that summarizes the whole topic. So when we have a large message that we want to encrypt, this topic of modes of operation comes into consideration. We have to consider which mode of operation are we going to use. And this mode of operation could be divided into two major categories. There is deterministic mode and the probabilistic mode. Now, deterministic mode, this is the simple idea that comes to mind when you have a large message. So the way you will go ahead and do it is you basically take the big message, chop it into blocks, and encrypt each block separately, independent of the other blocks. So this is the very simple way to do it. It is very efficient because you can make it in parallel, but you may be subject to substitution attack, and that's what we discussed before. So this mode of operation where you encrypt and decrypt each block separately, we call it electronic code book, ECB mode. And here, this is deterministic because if you feed the same text, the same plain text, you always get the same ciphertext. And this is not good from cryptography perspective because it opens the door for substitution attacks. Now, to overcome this, we have to come up with a probabilistic mode. Probabilistic mode, which means I may feed the same plain text, a message, and every time I get a different ciphertext. And this is a much better encryption mode. So for these modes, we have two subcategories. We have the block models of operation, and we have stream modes of operation. Block modes of operation and stream modes of operation. Now, the block mode of operation, we have this Cipher Block Chaining mode. Cipher Block Chaining mode. If you recall, just a quick review, this is the Cipher Block Chaining mode. Very simple. All you do is...
Initiate a vector?
Yes. So for the first block, the first always have special treatment. So the first block, the way we will encrypt the first block is that we will use initialization vector, which is a random number, has the same size as the block we want to encrypt. And what we do is we take our plain text, we do XOR with the initialization vector, and then the results of this XOR, we go ahead and encrypt it using the key. This will give us the ciphertext. This is the processing of the first block. Now, subsequent block, we take this ciphertext of the first block and feed it and XOR it with the second block, and the result of that XOR, we go ahead and encrypt it. And we keep doing this for the remaining blocks. So to generalize this is how we can generalize this. So if I want to encrypt any block I, if I want to encrypt any block I, what I do, I first XOR it with the ciphertext of the previous block. Yes, and then go ahead and do the encryption using the key. For the first block, before I go and do the encryption, I XOR it with an IV, initialization vector. And this initialization vector is a non-secret. I will pass it along. Yes, I'll pass it along to the recipient. The only condition for the IV, it should be in nouns. You will hear this term a lot in security. We call it a nouns. And nouns. This is a number only used once. We use this number once only. So we don't repeat using this IV. And it is a non-secret. If we use a true random number generator or crypto secure random number generator, this will produce a unique number that will not repeat. Okay. So this is so in here, even in this mode, we are still using the cipher text, the algorithm of the cipher for encryption. For example, here, the encryption could be using something like DAS or AES. So in here, we are still using the block cipher for encryption and decryption. Now, another mode of operation, what we do is we use the block cipher to generate a key, and we convert the whole encryption and decryption as a stream cipher. So we no longer use the block cipher for encryption or decryption. We use the block cipher for generating a key. And then the generated key, we XOR it with the plain text to produce the ciphertext. And here we have three modes. Is the output feedback mode, there is the cipher feedback mode, and there is a counter mode. So here is where we stopped. I tried to explain it. Many of you didn't get the idea. So let me give it another go. So here, the stream modes of operation. It might not come to mind as a first solution, but this is a really smart idea. What we do in here, we take the cipher block or the cipher algorithm, which could be DAS and AES. We don't use it for encryption. We use it for key stream generation. If you remember the stream cipher, if you remember the way the stream cipher works, we have the key generator at both sides. It generates keys, and then we XOR them with the plain text to produce the ciphertext. So here is the idea. I think I changed the diagram to make them, I took this one from Wikipedia. I just didn't have the place here to put the acknowledgement, but I put it in the last slide. This is well explained in Wikipedia. This very nice diagram. So what we have here, first, for the first block, we go ahead and generate an initialization vector, which is a random number, has the same size as the block we're trying to encrypt. Then what we do with this initialization vector, we go ahead and encrypt it using the block cipher. It could be DAS, it could be AES. And of course, encryption will take a key as the input. Now, this will produce a block of text that is encrypted. What we do with it, we XOR it with the plain text. This is our plain text we're trying to encrypt. We XOR it with the plain text, and this will give us the ciphertext. So notice here very carefully that the block cipher is not used to encrypt the plain text. It is used to encrypt initialization vector, which is basically, yes, a key string. Then what I do with this key, I feed it to the next. For the next block, I take the key used for the previous block and encrypt it again. Encrypt it again. This will give me another key, and I XOR it with the plain text to produce the ciphertext. And then I take that key and use it for the next block. So for the next block, I take the previous key, encrypt it, and then use the output to XOR it with the plain text to produce the ciphertext.
Next operation will be bit by bit?
No, in here, the operation is block level. So it's not bit level, it is block level. Of course, the XOR will be done at the bit level, the XOR at the bit level. But all this encryption and decryption, the encryption of the key is using the algorithm we've seen, how DAS or AES work. So it is block size. For DAS, it works at the bit level, for DAS, if you remember. While for AES, it works with byte level. But that is basically the inner working of the algorithm we're using. The key idea here, is that we are building a stream cipher from the block cipher, from a block cipher. This is the key idea, which means we are using, another way to say it, we are using the block cipher to generate a key stream, SI, and then we take this key stream and we XOR it with the plain text to produce the ciphertext. And the key stream, the output of the output of this encryption, we feed it back to the next for encryption, the next block. That's why we call it output feedback mode. Output feedback mode. Okay, have a look at this. This is the visual representation of encryption, and this is the algebraic representation. So take a look at this. For the first block, what we do is we take an IV, which is a randomly generated number, we encrypt it using the key, and that will give us the first key the first key in the key stream. The key stream is a set of keys. For each block, I have a key. So for each block, I have a key, and those set of keys, I call them the key stream. So the first key is generated by encrypting the IV. And then what do I do with this generated key? I XOR.
Send it to the next.
Yes. So first I use it for encrypting the first block. Yeah. And then for subsequent blocks, I use the previous key, encrypt the previous key, and the results, which give me another key, and that key I will go ahead and XOR it with the plain text. And I do this for every block except the first one. The first one I use the IV. The subsequent blocks I use the previous key, encrypt it, produce another key, and do the XOR. Now for decryption, you need to be very careful. Remember the stream cipher. In a stream cipher, the key generator is exactly the same. Exactly the same. So don't fall into the trap in here. We are not decrypting. We take the IV again. We take the IV, we encrypt the IV, it gives us S1, and then I use that S1 to encrypt. So it's exactly the same steps or same algorithm I use for encryption and decryption.
This one in reverse.
We don't reverse it. Have a look, take a look very closely. It's exactly the same. So I go ahead and encrypt the IV, and that will give me S1. What do I do with the S1? I XOR it with the ciphertext to get the plain text. This and this are exactly the same. Even the subsequent block is actually the same. I encrypt the key used for the previous block. The generated key, I XOR it with the ciphertext to produce the plain text. You need to be careful because in here we are converting this to a stream cipher, and by definition, the stream cipher, the key generation is exactly the same. So here we don't use decryption. We just you encrypt the key, generate another key, and XOR it with the ciphertext to produce the plain text. So be careful here. This could be a tricky exam question. That here we are encrypting again the IV for decryption. We are not decrypting the IV. We are encrypting it to generate the key stream. Okay, so is this clear, the output feedback mode? Is clear, or should I explain further? Is this clear to everyone? So the key idea is this one. We are using the block cipher to build a stream cipher. We are using a block cipher to produce a stream cipher. Okay, so this is one mode, output feedback mode. This is still cannot be done in parallel because there is dependency. You have to do the first block, then second block, and so on. So it can only be done sequentially. Another way of doing it, yes?
We could send the key, at the same time we could encrypt the text.
What do you mean send the key?
After we done from encryption of the key, we could send it, and at the same time, another process will just encrypt the key with the XOR the key with the plain text.
You mean send it to the recipient?
Yeah. So basically.
Yeah, no problem. Yes. But what I mean, let's imagine, let's just keep it simple. Let's say we have just a file. We want to encrypt a file on the same process. We are not sending it anywhere. So to encrypt the file, we have to do it sequentially, one block at a time. Now, what we do with that block, you can store it on disk or send it somewhere else. That's fine. It's up to you what you will do with it. But the actual encryption and decryption is sequential. It cannot be done in parallel because there is dependency between the steps. the output of the first step is fed to the next step, and so on. So it is sequential. So this is the output feedback mode. The other mode is the Cipher feedback mode. Exactly the same. We use the block cipher to produce a stream cipher. The only difference is that in here,
Use the ciphertext and the key.
yes, we use the produced ciphertext and feed it, encrypt it again to produce the key for the next block. And then we produce this ciphertext that we produce for block 2. We use it as a key, not as a key, sorry. We use it as an input to encrypt it again and use it as a key for the next block. So it's very simple. Like you can just look at it here. So for the first block, I'll generate an IV, which is a random number, has the same size as the block I want to encrypt. I take that IV and encrypt it using DAS or AES, whatever the block cipher happened to be. Of course, whenever I say encryption, it must take the key as an input. And then what I do with this output, I XOR it with the plain text to produce the ciphertext. Then this ciphertext, I use it as an input for encrypting the second block. So I take the ciphertext of the first block, go ahead, encrypt it again to generate a key. And then what do I do with this key? XOR it with the second block plain text to produce the ciphertext. And then take that ciphertext, feed it to the next block, and so on. So that's basically the idea. This is visually how it looks like. Now, in terms of equations, so what I'm doing here, I encrypt the IV and then XOR it with P1. This will give me the ciphertext of the first block. Then, for subsequent blocks, I encrypt the ciphertext of the previous block and then XOR it with the plain text. Now, take a look, very careful again. For decryption, I do exactly the same because remember, this is now stream cipher. In a stream cipher, the key stream generator must be exactly the same. So in here, have a look. What I'm doing here to produce the plain text, all I'm doing, I'm encrypting the IV. Look at this, it's exactly the same. And XOR it with the ciphertext to produce the plain text. This is what I do for the first block. For the subsequent blocks, I encrypt the previous ciphertext and XOR it with the ciphertext I want to decrypt, and I get the plain text. Yeah, that's basically the idea. So this is still sequential. It cannot be done in parallel because there is dependency between these steps. The output of the one step is the input of the next. Yes, please.
Normally in sequential, the error percentage will be higher than the parallel, right?
Sorry, the error?
The error percentage, like, for example, if we mistaken the second or third step, everything after will be...
Yes. If we have to redo encryption for some reason, or there is a transmission error, or there is a change of the plain text. Let's say one plain text block change. We have to encrypt from that plain text that changed to the remainder of the message. So, yeah, that is a good point. So it's clear here what we're trying to do here. We are using the block cipher to produce a stream cipher. And in the output feedback mode, we are encrypting the key, and then the produced key stream, we XOR it to the plain text to produce the ciphertext. We take the key again, we feed it, we encrypt it again for the next block, and so on. That is called output feedback mode. Another way of doing it is instead of feeding back the key, I feed back the actual ciphertext. And this will become Cipher feedback mode. The last mode I want to cover here is the counter mode. So let me show it to you visually, and then we come and see it here. So in the counter mode, again, I changed the diagram to the Wikipedia diagram. It's much clearer. In here, what I have a counter. So this counter is made up of, let's say, this is my IV. Another name for it is the nonce. Nonce means a number that I use only once. I don't reuse it again. So this nonce, let's say I have, if I am using DAS, for example, this nonce will be 64 bits. So what I do is I just take, let's say, 64 bits. How many bytes? 16, yeah? 8. 64 divided by 8 is 8, yes? 8 bytes, yes? 8 times 8, 64, yeah? So what I do is 7 bytes. I take 7 bytes from the IV, and 1 byte is the counter. Counter is just a number that 0 increments 0, 1, 2, 3, 4, 5. So for each block, I take the IV, I take the 1 byte, basically the last byte of the IV, instead of using the, okay, if the IV, if I am encrypting, let's say, if I am using DAS, so the initialization vector will be 64 bits, yes? So what I do is the last byte, I use it for the counter, and the remaining bytes will be a random number. And then that random number, have a look here, it is exactly the same for all the blocks. For all the blocks, it is exactly the same. What is different for each block is the counter is incremented. That's why we call it a counter. 1, 2, 3, 4, 5, 6, and so on. And all I do, I take this random number. It is really still a random number because the first part is random. Only the last byte is a counter. Then I take that, encrypt it using the block cipher. It could be DAS, it could be AES. Encrypt it, and then the output of the encryption, I XOR it with the plain text to produce the ciphertext. And I do the same for the remaining blocks. All I do here, every time for every block, I increment the count. First thing, yes, if let's say we have a large message or a file, if one block change, we just need to re-encrypt that block that has changed. That's one advantage. But more importantly, we can now do the encryption and decryption in parallel, because there is no dependency, there is no feedback. It's not like the other mode, the output mode and the Cipher feedback mode, where we take, let's say, the key and feed it back. There is no feedback here. Each block is independent, and we can generate these keys because it could be very simple. For each block, we know how to generate the key for, not the key, sorry, this input to the encryption. This input can be done easily in parallel. We don't need to do sequential. Sort of clear, this counter mode. So in the counter mode, let me just say it one more time. In the counter mode, what we have is the counter is made up of concatenation of two pieces. A fixed nonce. A nonce is like initialization vector. It's not another name for initialization vector. Plus a variable counter, which gets incremented by 1 for subsequent blocks. Okay, so let me now show you the equations for this. So for any for every block I want to encrypt, what I do, I first compute the counter, which is, as I said, part of it is the nonce and part of it is the counter. The counter is nothing but an incremented number from 0 to the number of blocks. I take that counter, encrypt the counter. Encrypting the counter will give me a key stream. And then what I do with this key stream, I XOR it with the plain text to produce the ciphertext. That's basically the idea. In here, because we don't have any feedback, it can be done in parallel. The implementation could be fast and could be parallelized to improve the efficiency of the encryption and decryption. So I hope it is clear. So all these three modes, what is common between them, the cipher feedback mode, the output feedback mode, and the counter mode, what is common between them is that all of them, we are using the block cipher to produce a stream cipher. We are no longer using the block cipher to do the encryption and decryption. Instead, we are using it to produce the key stream. And when we are producing the key stream, we are producing in a blockwise fashion. So every iteration, we are producing a key that has the same length as the plain text block. And all we do, we export it with the plain text to produce the ciphertext. And for decryption, we do exactly the same. We encrypt it again, we produce the same key stream, and we XOR it with the ciphertext to produce the plain text. That is basically the idea. And this is really summarizing. This table again is summarizing all the major modes of operation that we have covered. So the first one is the ECB, the electronic code book. So in here, what we see here is, as I explained, we take the message, we chop it into blocks, and we encrypt and decrypt each block independently. Super fast, it can be done in parallel, but it comes with the risk of substitution attacks. And because it is deterministic. Deterministic means every time I feed it the same plain text message, it produces the same ciphertext. Now, to remedy this, we can go and do CBC, which is a Cipher Block Chaining. So in CBC, what you do for the first block, you go ahead and produce an IV, an initialization vector. You XOR it to the plain text, then you do the encryption. And for the subsequent blocks, you take the previous cipher, you XOR it to the plain text, and then you go ahead and do the encryption. Now, for these three other modes, we are using the block cipher as a stream cipher, which means the block cipher now is used to generate a key stream. All we do, we XOR the key stream with the plain text to produce the ciphertext, and we do the same for the decryption. So, in most cases, don't go with the ACB because it's vulnerable to substitution attacks. Consider other modes. Particularly, it looks like the counter mode, like it has the advantage of both. It gives you probabilistic cipher, or probabilistic ciphertext, plus it can be run in parallel. So it seems to me like the counter mode is the most it gives you that extra protection from substitution attacks. At the same time, you don't need to, it's efficient because you can run it in parallel. Many of these diagrams, I took them from Wikipedia, and there's a Wikipedia link. It has all the details, much more details than what I covered, but these are